Ever stop and think about how your computer actually works? I mean, really think about it? Your phone, the screen you're looking at right now, deep down, it's all speaking this kind of secret language. And today, we're going to learn the basics of that language. We're going to crack the code.
It all boils down to this one simple but honestly pretty profound question. Inside every single one of your devices, you've got billions of these teeny tiny switches that can only be on or off. That's it. So how in the world do those two simple states create everything? Photos, videos, entire games, all of it. Well, that's the magic we're going to decode today.
Okay, so to get to that answer, we've got to start with one really fundamental concept, and that is the whole idea of a number system. Now, don't let the term fool you. It's basically the set of rules, the framework for how we and how computers count and represent, well, absolutely everything.
Yeah, I know number system sounds kind of academic, right? But it's something you literally use every single day without even thinking about it. It's just a set of rules for how we write down numbers. We have our system, the one we all know, and as we're about to find out, computers have a totally different one.
All right, so here's our roadmap for this whole explainer. These are the four big players, the main number systems in the world of computing. And I get it, this might look a little intimidating at first. You've got different bases, different digits, but trust me, it's way simpler than it looks. We're going to start with the one you already know like the back of your hand.
Okay, let's kick things off on familiar ground. We're talking about the decimal system. This is the language of numbers we all grew up with, the one we learned in school. You could say it's our native tongue when it comes to counting.
So why do we call it base 10? Well, it's pretty straightforward. It's because it uses 10 unique digits, 0 through 9. As soon as you hit 9, what do? You roll over, add another column, and you get 10. It's completely intuitive to us, right? I mean, it probably helps that we have 10 fingers to count on. This is the human standard, plain and simple.
So if decimal is our language, what's the computer's? Well, it turns out the computer's native tongue is actually way simpler. It's time to start thinking in binary. And wow, the difference is pretty stark when you look at it side by side. We've got 10 different symbols to play with for any number we can think of. A computer, it only has 2, a 0 and a 1. That's it. Everything a computer does, I mean everything from complex calculations to just putting this image on your screen, has to be broken down into a long sequence of just those 2 digits.
So you have to ask, why? Why only 2 digits? The answer is really the most important part of all this. It's because it maps directly to the physical hardware. A computer is just made of billions of these microscopic switches called transistors, and a switch can only be in one of 2 states. It's either off, which we call 0, or it's on, which we call 1. That's literally it. This is the absolute fundamental building block of every piece of digital information in the world.
Okay, so if computers are perfectly happy living in their world of zeros and ones, why on earth do we need these other systems like octal and hexadecimal? Well, here's the twist. They aren't for the computer at all. The computer doesn't care. They're for us. They're actually really elegant solutions to a very human problem.
And here is that problem. To represent anything even a little bit complex, like say the color of a single pixel on this screen, the binary numbers get insanely long. Just imagine you're a programmer and you're staring at pages and pages of just ones and zeros. It would be an absolute nightmare. You'd go cross-eyed trying to read it, write it, or find a mistake. We humans we're not built for that.
So this is what led clever programmers to develop some shorthands. Think of them like cheat sheets. Systems like octal, which is base 8, and way more commonly hexadecimal, which is base 16, were designed for one reason: to take those massive binary numbers and squish them down into a much more compact, human-friendly format.
Now, of these 2 shorthands, hexadecimal is, by far, the one you'll see everywhere in modern computing. And because it's a base 16 system, it needs, 16 unique symbols. So what do you do after you've used up our normal digits, 0 through 9? You just keep going. It cleverly adds the letters A through F to stand in for the values of 10 through 15.
And the way this works is actually kind of beautiful in its simplicity. See, there's this really neat mathematical relationship where every single group of 4 binary digits can be represented by just one hexadecimal character. So you can take a giant, scary-looking binary string, chop it up into little groups of 4, and then just translate each little chunk. It's a perfect shorthand.
And this slide right here, this shows you the payoff perfectly. Just look at that binary string on the left. It's kind of clunky, right? A bunch of ones and zeros. But in hexadecimal, that exact same value becomes the simple, clean F5.
I mean, come on. They're both saying the same thing, but one is so much easier for a person to read, write, and remember. And that right there is the whole reason hexadecimal exists.
Okay, so let's start to put this all together. We've looked at 4 different systems, but the single most important thing to take away from this is that they are not 4 different things. They're just 4 different languages, all used to talk about the exact same numbers. Yep, this is the key takeaway right here. It's just like how 5 in English and cinco in Spanish mean the exact same thing. The number we call 10 in our everyday decimal system is the same exact value as 1010 in binary, and the letter A in hexadecimal. They're all just different ways to write down the same idea.
And this table just ties it all up in a neat little bow. You've got decimal, that's our language, for humans. Then you've got binary, that's the machine's true native tongue, based on those simple on-off switches. And finally, octal and hexadecimal, they're the coder's shorthand. They're the bridge that lets us humans talk to the machine without going crazy. Each one has a really clear, really important job to do.
So think about it. What started as just a simple on or off becomes a whole language. A language that we've used to build everything from our favorite apps to incredible digital art to a network that connects the entire globe. And that really leaves us with one final big question. If this is what we've managed to build with a language that only has 2 letters, what other amazing things will we learn to say next?